All right, so I have this class starting at 9:35, so I'm going to go ahead and get started here. My plan of attack is on the board here. I'm going to start off with an instructor introduction, kind of introduce myself. And after that, I'm going to talk about the course as a whole, and then what a specific class time kind of looks like, and then we'll get into our first topic, integration review. Now, but a couple things right away to note here. So I opened up a little recording device, and I have a little open mic up front. I'm going to be recording all these lectures, and I'll post them to YouTube right after class. So that way, if you hear the lecture, maybe you missed something, or maybe you just want to go back and review, you're always welcome to go back to YouTube and just rewatch the videos. Now, that doesn't mean you can skip class and not come to class and just watch the videos. We're going to be doing a lot of interactive stuff in class, so I really want to give you problems, have you work on them, maybe work in some groups, do stuff like that. We're going to have quizzes in class, so you really need to come to class. This is just something you can refer back to. Or, if something happens where you're sick and you miss a class, then it's kind of a nice tool. Any questions about that at all?
What's the channel? What's the name of the...
I'm going to post it on the Canvas page, so you can search for me, but right on the Canvas page there'll be a YouTube page. I'll put the entire playlist there. So after class, I'll just close it. It takes about an hour and a half, 2 hours to process the video and then actually get loaded. And then it'll automatically get added to that playlist. Okay. Other questions? All right, so first off, I guess this is Calculus 2. So if you're not in Calculus 2, it's the wrong class. So we'll start off with an instructor introduction. So you kind of know who I am. There we go. So, 3 different parts of this: academic, personal, and professional. Academics, I graduated from Northern Michigan University with my undergrad in math education. After that, I came here, did a master's in mathematics, and now they hired me on as a lecturer here. So you don't have to call me doctor, professor, I'm just Mr. Gregerson, so let's get that out of the way right away. I also run the math lab, so you've probably seen my name before if you went to Calc 1 here as the math lab director. Personal, I did 4 years in the Marine Corps a long time ago. That's probably where that plan of attack comes from to start with. I got married after that, then I have 3 lovely children there. So I always like to show them off every chance I get, so it's a little bit about me. The last thing, professionalism is really important to me. So I'm going to come to class very prepared. Hopefully every class period I'll have my notes up here and all sorts of stuff going on. But I really expect the same from you. To kind of put forth the effort in this class. It always feels not so good when I'm putting a lot of work in and you're not putting as much work in. So I just asked you to kind of match my effort level here, and then you'll definitely succeed in the class. That's one thing. Also, as you can see, I love technology, so I use a lot of technology. I encourage you to do the same thing. We're going to do a lot of Mathematica stuff in here. It'll kind of pair with the lab, but also just to help us do stuff in class. So I encourage you to do that. You'll be able to use your TI-89s or whatever other calculator you have on your exams. So make sure you know how to use them. Those are the tools we use in real life. So I want you to use those tools. If you're in class and you have your computer and you could take notes like I do, if you were talking about some topic and you want to Google it real quick, feel free to do that. That's okay. At the same time, don't be texting on your phones or doing that stuff. That just drives me nuts, right? So I put a lot of work into lessons, so it's kind of irritating when people are texting and doing other stuff during class. Any questions about any of that? Okay. All right, so the one other thing about that academics is I did my undergrad in math ed, not just math. So they gave us a lot of pedagogical tools to teaching. And one of the first things they said there was, one of the things instructors usually forget to do is wait when they ask questions. I'm sure you've had that in a lot of math classes, right? What do you think about this? And then they tell you what they think about this, right? They said that if a good wait time should make everyone in the room uncomfortable. So that's probably going to happen, so just kind of expect it. I have my coffee here. I'm going to pretend that I'm waiting for pedagogical reasons, but really I just want to drink some coffee, so that also will happen. Okay? So any questions? But I really do want questions. I mean, it's really important, I think, to communicate in this class. Remember, it's your grade. All right? It's not anybody else in this room's grade except for your grade. So you need to worry about what you understand, don't understand. If you have a question, ask it. Right? Other people have the same questions. They're just shy to ask or something. So make sure you ask your questions. All right. Course introduction. All right, so I'm sure most of you are coming today in an uncomfortable position already because you're kind of blind as you come in, right? There wasn't welcome emails send out, and all these other kind of information. And this is actually a new course that we're going to do this semester. It's going to be different than the other Calculus 2 courses. If you had Calc 2 before, this one's going to be different. All right, so we're going to go through everything step by step here and really walk you through everything. So we're going to start with the Canvas page. Talk about the schedule, different pages on there, and the syllabus. So here's our Canvas page. That got published this morning, so you should now have access to it. You're going to open it up, and this is the page you're going to get to. Very good. Everybody see that all right? Sure. All right, so this is the main page. A couple things that we're going to be using a new textbook. We're piloting a textbook this semester. Our textbook is Calculus for Science and Engineers by Briggs. Okay. Now, because it's a new textbook, and normally you have to buy an expensive calculus book, but at least you can use it through Calc 1, 2, and 3. This one you probably won't be able to use through Calc 1, Calc 3. You don't have to buy it. We're going to provide you an online copy for free. So on here, the very first thing is a Getting Started flyer handout thing. And in it, it's going to have the access code that you can use to access the book online and the online homework system that we're going to use. So all that's going to be provided to you for free. Okay, so all that stuff is in the Getting Started handout. You're welcome to purchase a hard copy, but it's a calculus book, so it's expensive. Of course, you're welcome to do that. And I would encourage you, there's 2 different versions of the text that we're going to talk about when we go more to the site. One is actually one built into a Mathematica-ish thing, which is really neat because they have a lot of manipulates you can move around. The other one is an HTML browser. But I would also encourage you, feel free to print those things out. Right? Keep a little notebook if you want, print it out if you want a hard copy as well. Okay, so this is the main page. That's what the Get It Started thing is. This is the link to the YouTube page. If you click on this, there'll be a little box there that's going to host all the videos. Right now it's empty because this is the first video. Down here it says course schedule. So we'll look at that real quick. Kind of access this, but to get a sense of what we're going to be covering, it's the summer, so it's fast-paced. Calc 2 is always fast-paced because there's lots of stuff we have to cover. But in the summer, it's a condensed schedule, so it moves pretty fast. So we're going to be covering 2 sections a day, a lot of days. Calculus is too fast for us to teach you everything in class. So you are expected to prepare for class, learn some of it on your own, and then we kind of hash through the rest during our class time. Right, so there's going to be preparation time that's required. Of course, there's a lot of class time where we're going to work on stuff. There's going to be that follow-up time that you need to expect also. In normal class, they say you should be working at least at a minimum of 2 hours for every hour in class. Now, once again, you condense this because this is not a normal class hour. You should be working at least 3 hours every day in this class. So just expect to do that. So the exams are already on here. They're going to be exams right in class in this room, nothing in the evening or anything like that. So we have an exam at the end of the 3rd week and then at the end of the 6th week. There will be a cumulative final at the end as well. Once again, for all those, you will be able to use your calculator and stuff on. All right, so that is the schedule page. Get over there. And the last thing is a resources page, which is right now empty. This is where I'm going to dump the solutions to quizzes as we take them, and also my Mathematica notebooks. We do stuff in class. I'll just dump notebooks there, and you guys can access them if you want. Okay, any questions about this home page? All right. So that kind of covers all the little pages around there. Next, we'll go to the syllabus here. Okay, for the most part, it's a standard syllabus-looking thing, right? So it's going to have name, office hours, all that stuff. Office hours are right after class, from 11 a.m. to 12 a.m. right down the hall. Feel free to stop by then. I'm also going to be there before class. I usually get in probably around 8-ish at the latest, so you should be able to see me then as well. If those times don't work, let me know, and we will personally schedule some other times as well. My email is on there. Talks about the text, how we're going to be piloting this text. Talks about the general course objectives. A lot of this is what we want to do by the end of the course. I encourage you to seek help. The Learning Center does have office hours this semester. They're pretty short, I believe, but they do have hours, so make sure you check in there. Fellow classmates, I would really encourage you to get in study groups. Just decide that right after this class you're going to go to the Learning Center or to the math lab and just find space and sit down and get in groups and finish stuff. I always encourage that. Attendance, I'm not going to be taking attendance or giving you a score based on attendance, but it's important. You'll be able to make up quizzes. If we have quizzes in class, you need to be here to take those quizzes. Homework, we will be using an online homework system that we're going to look at right after we're done with the Canvas page. It's the My Math Lab through Pearson. So we're going to show you how to access that and do all that stuff. The online homework will count as 10%. It's a little bit different than Wiley in that they don't give you like just 3 attempts. They really give you unlimited attempts on this, and we'll talk about that when we see it. But it's really just something that if you keep doing it, they just want you to learn the material. So they will give you as many attempts as you need. But remember, it's exam preparation. The bulk of your grade is going to be exam-based, so the homework is preparation for the exam. So you can probably get a really good homework grade if you kind of zip through it and game it a little bit, and I'm sure you can get a perfect score. It's all going to be preparation for the exam. That's really where everything counts. Math Lab is going to mean a lot of things. There's the Math Lab room, which is right across the hall over here, Fisher 331. My Math Lab just happens to be the name of the online homework system from Pearson. And of course at Tech we have a Math Lab, which is the Mathematica instruction for the course. So we do have that attached. You should have already got a kind of welcome email about that. Calculus 2 is going to be a little weird because we want to match that lab content up with this new kind of piloty course. So in the past you've probably seen all your assignments right away. And now if you go on there, you probably only see the first 2 or 3 Mathematica assignments. And those will kind of be added as you go along. Feel free to ask Mathematica questions in this class as well. As kind of the Math Lab director, I love Mathematica, so if you're stuck on a lab question, feel free to bring it up, and it's all related to calculus, so it'll all be useful. 2 exams and a final. We have quizzes in class. There's the grading breakdown. Again, this is on the Canvas page, so you can look at this at your discretion here. Work hard. Don't fall behind. Right? The quicker, if you feel yourself falling behind, come and see me, please. The best thing you can do is communicate with your instructor. I encourage you to come in. You can set up a weekly meeting or a daily meeting, whatever it takes. So make sure you communicate. All right, that's the syllabus. Any questions on the syllabus? Okay. All right, so let's go to the home page and see what that online homework system looks like. All right, so you're going to open up this document. So one thing that's kind of weird about this homework system from an instructor standpoint is they actually don't have a student view, like a button I can push to get rid of the instructor tools and see exactly what you see. So instead what they want you to do is create a separate account as a student so that you can kind of see what the students see. So I'm just going to do that right in class today. So you can actually see the process of registering and putting in your code and all that kind of stuff right away. Okay. So this is the document you're going to open. It's going to have your course ID right here. It's going to have the access code that we're providing for you for free. And it's going to have steps to get started here. So we're just going to follow the steps here. It says go ahead and go to this website. So I'm going to click on that. Did you open? There it is. Okay. I'm going to flip this around and make it a little easier for myself. Okay, so there's the website. See the next instructions. It says under the large register section on the right side of the page, click the student button. So let's do that. Student button. Do you have our 3 things? Do you have some sort of email? Do you have a course ID? Do you have an access code? Well, we have the course ID and the access code right in the thing. So all you need is a valid email. I'm going to register now. Enter your course ID. So this one is going to look like Gregerson and 68255. 68255. And you make up a username and a password. So my username will be Jason. See if I can remember that. create account. All right, so you're going to fill all this stuff in. Oh, should we do this real quick? Sure. Okay, you're going to fill all this stuff in. The next prompt is going to ask you for your code. And from your code, you'll just enter in that access code. Yeah, let's just do it. Uh-oh. No symbols. Kind of tricky. There we go. Except I did not want to learn anything else, and I read all that. I really did. You just didn't see anything that looked like. Okay. Access code. Right over here. Access code. Now we have our access code from this thing. Let's see if we can do this. We got WSCMMV. Oops. Setup. Rodeo. Roomba. Meat. And dice. All right, well, I'm going to check on why that doesn't work. I typed it correctly, right? Did I miss anything? All right, there must be some missing digit here at the end. All right, so I will tweak that and get that out right after class. Sorry about that. All right, so then what we will do is it will look like this, essentially, without these little hidden views right here. These are two things that are hidden that you normally wouldn't see that I can see on mine. All right, but when you open it, you should come to this course homepage. All right, from this course homepage, you'll have some basic stuff from Pearson. You can check your browser. I'll give you little tutorials if you're worried about this. This Pearson tutoring service, I think it's something you have to pay for, so I kind of investigate that if you want. Really, the main thing on here is this calendar. It shows you little assignments that are coming up in the upcoming week. Right now, I only have 2 assignments scheduled. The rest will be added kind of as I develop the homework as we go. So you can kind of hover on those and see what to do. So tonight, so become familiar with the exercise area, and this is like an orientation of the homework. So you just click on this, and it will tell you how to enter things. You know, online homework systems are a little quirky, so this is designed to prepare you for that. And then tomorrow night, we have our first real assignment. This is the Chapter 5 review homework. My plan for homework is that if we cover a section today, then the next class period, that night at midnight, that's when it's due. So you will always have one class period come and ask questions from that homework after we've covered it. That's the general schedule. So that homework is there. This one is here. You can click on these or also go to the homework page. All right, so on this page we have the ebook. This is just the HTML version. There is the homework list. It has all the homework assignments you can click on and then follow the instructions for completing them. There is the grade book. The calendar just lists the homework due dates. Study plan is just a list of extra problems that you can work on to get better. You're not required to do anything from the study plan. And there's a bunch of little options in the study plan that I have to explore myself as I'm getting used to the platform as well. So you can kind of use that if you want to explore it. Otherwise, you can ignore it. Tools for success is a bunch of tools for success. Right, a bunch of optional things that flashcards and things you can play with if you want to play with. Multimedia library would be the same thing. It'll be videos and other tools that you can use at your discretion. Chapter content is really the thing that we're probably going to use kind of the most if you want. It has the chapters we're going to cover here. We're just doing a one-day review of Chapter 5, so mostly we'll go to Chapter 6 here. You can open that up. It'll have all the sections. You click on a section. It will tell you to read the book. Here are some figures if they apply. So sometimes there's some sliders, stuff that might help you visualize stuff. A study plan is kind of for your own benefit. And then instructions to complete the online homework. So you would read the book, play with the tools if you want, and then after class go down to homework and do the homework. Now this book is different than the other book. This book is the Mathematica version of the book. So this would be that section, 6.1. And it really is just what the text covers. It has all the words, but it's in a Mathematica thing. You don't have to have Mathematica installed to open it. It runs from your browser, but it has all the functionality. So it has little sections you can open. It'll have the text just like it regularly does. But every now and then they'll have interactive sliders and things you can pull to change graphs and things you can compute as well. All right, so you can open up and read from there, or you can read from the HTML version. Okay, and you have to have internet access to access this. Any questions about the text or the platform? Yep.
Is there any way to look at the text when we're not connected to the internet, say we're on the road?
What I would do is print them out. So you can either open the sections and physically print them, or you can open the sections and print them to a PDF or something like that. And if you were to do that, I would probably do that from the HTML version. I guess that's all the way open, whereas this one you have to open it up and open up all the sections and that kind of stuff as well. So I would go to the HTML version, either print to a PDF or just physically print. Okay. Other questions? Now this is a new platform, right? So I haven't played with it much myself, so it's going to be a learning curve for you and for me. So the benefit to you is that we have unlimited attempts to this, so it really should be something you can boost your grade from. And if there are any problems that come up, even with the unlimited attempts, I didn't understand this question, we're going to talk about it, and I'm going to be very lenient with the grading. Right? I have no problem saying, this question was weird, I'm going to give everybody credit for it. So that's how we're going to go through the homework. Okay. All right. So that is my math lab. I'm going to have to check on that code. All right, now what does an actual class look like? There's really going to be three phases of class. There's the before class, the in class, and the after class. Oh, one other thing from those platform. Certain sections, this section for instance, also has a video for that section. And that is required watching. So I'll try to give you the heads up when those sections are coming up. That is required prior to class and preparation for class. Every day in class you should be reading the section before we cover that content. So that's the before class. Before class, in class, after class. Before class, you need to read the section. You need to print any notes. If you want to print the section or look at any of the resources they have on there, do all that stuff. Watch the video if it's available for that section and do that good preparation. We will have preparation quizzes based on the reading. We just don't have enough time in this course for me to go through every section and say, section 6.1 covers this, 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 and go through all the stuff. You have to prep. We have to use our class time to get the hard stuff, answer questions, work on stuff. So you have to do that reading ahead of time. So make sure you're preparing for class. There will be prep quizzes based on preparation. They're not going to be hard prep quizzes. Right? I'm not expecting mastery. It's hard to read math books. Right? I think we all know that, right? So I'm expecting you to preview the content, get the big ideas, that stuff that's in boxes or bold letters, make sure you get the definitions, and try a couple of the practice problems or go through some of the examples. And I'm going to ask you the basic questions from the section. Okay? That's what needs to be done before class. In class, then, we're going to do an overview of the reading. Okay? Like it says in red there. Here's what we know. Here's what we know from the reading. This, 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 and this. And that's your opportunity to say, yeah, I know that was in there, but I didn't get that part. All right, now let me focus on specific things to talk about. All right, I'm going to open every class period with questions. Questions from the previous homework, questions from the reading. That's what we're going to start with. Then if there's a preparation quiz, then we'll do the preparation quiz after you've had time to ask questions. Okay? After that, we're going to do a lot of practice problems. We're going to work in class, not just listening to you talk off class. We're going to do some practice stuff. We're going to extend lesson ideas, try to deepen the understanding or apply them. We'll also have quizzes, problem sets, all that kind of stuff. Hopefully some group work. You will need clickers for this class. How many people already have clickers? Okay. If you haven't needed them yet, I am almost 100% sure you will need them in other classes at some point. So, you can buy them online pretty cheap, or you can buy them at the bookstore, I believe. I'm not going to take grades with them, so don't worry if you don't have it for the first week. Mostly do polling in class. But they're a good way for me to see if we're following, if I need to go faster or slower, and get a sense of what we're really taking in.
We set those up online, or?
I'll do a roll call at the beginning of some classes after I'm given time to get them. So you have to do that. After class, you have the homework. Homework is due 11:59 p.m. the day of the next class. Okay. And kind of the last thing about the introduction is this is a tough class. For a long time, Calculus 2 has been the class, right? The roadblock class that people struggle to get past to move forward in their programs. It's tough. It's tough content-wise because it's kind of scattered around a bunch of different topics. It's tough because it's a fast-paced course. And in general, you take it pretty early in your academic careers here, so it's getting used to college, and college can be tough transition from that. So the goal here is that we need to work together to succeed here. That's in class and after class. So working together in class means communication. It means asking questions. Don't ever worry about, well, I don't want to ask because he's on a roll and I don't want to slow him down. Please stop me. Ask. It's my job to manage the time. So put the pressure on me. Right? Ask questions if you don't understand stuff and let me worry about that other stuff. Okay? I guarantee your classmates will have the same questions and you're just getting somebody to ask them. Okay, and really, really, please stop by office hours. It's lonely otherwise. Just sit there. So, all right. So I get really excited about this. I want you to stop by, ask questions. It's kind of a blended class. It's new. I want to do something to really shake things up. And then I watched this video and said maybe I shouldn't.
Come on, stand on your desk. Up on your desk? She made it! Everyone, stand on your desks! Up, come on! Rise, rise, rise above the programming. All your lives you were told, don't stand on your desks. Well, why not? She's okay, go to the nurse, seize the day.
Okay, so I don't want to get too crazy in motivational here, so, okay. All right. That really concludes the warm-up stuff, the intro to class. Last chance for questions from the introduction. Questions about what class is going to be like.
The homework's going to be posted on Canvas?
The homeworks are going to be in that online format. So you just go to Pearson once I fix the code here. And you'll just go to homeworks. And so the one due tomorrow night is going to be this one. So you just select this one, blah, 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 blah. Uh-oh, do I have to read that, actually? Okay. Yeah, you don't have to do all these. That's a big review. Yeah, that one will be modified. That'll be more like this. This is the one that I went through. Yeah. Okay. So something like this will be, yeah, the size. So boy, that was scary there for a second. Okay. All right. So you go in here, then just go through the questions, and it'll be similar to other systems. They have their own little quirks about entering in values and whatnot, but you just put stuff in here. Okay. Other questions? Yep.
How soon do they become available?
As early as I can get them. So like I said, I'm kind of prepping the pilot course here. Normally this stuff is just kind of handed on from semester to semester. So this is the pilot to see if we're actually going to use this textbook in the future. So it's not fully built out. So right now I have the assignments set for the 6.1 and 6.2. And then tonight I'll probably post 2 more or 3 more, and I'll try to get it ahead as far as I can. But in general, I mean, I want to take maybe the next week and a half to get them all posted, and then you should have access to them all if you want to work ahead. Okay? So it's just a matter of me getting ahead a little bit. Yep.
Well, all the grades from this homework be posted to Canvas where we can see the whole layout, or is it-
Those grades will be in here, and the homework grade counts as 10% of your overall grade. So there'll be a slot in Canvas for your homework assignment, but that won't tabulate as we go. So you'll just have to say, well, I'm 90-ish% here. And if you want in Canvas, you can always put in your test scores. I don't know if you guys have seen that feature at all. So you can just put in 90% and kind of see how it affects the rest of your grade. But homework grades will be in here. All the other grades will be on Canvas. And at the end of the class, I'll port those in.
Is there a specific like page on this website?
Yep, there should be a grade book here that you should be able to go through right there. And it should have a list of all your scores. So I didn't do very good at my first one. So, other questions?
On the exams, calculators, the whole exam or just half?
Whole exam, even the whole time. You will, of course, have to show your work. So, if I will write the questions, assuming you have a calculator, and they will pull out those little pieces that I'm going to need. So, and some will say, show your work by hand, and I'll look through, and if I see confusing, the right answer, then I'll be suspicious. So. Other questions? Like I said, bring your questions from the homework. Normally I get a lot of homework questions. I did a little bit of piloting with the system in linear algebra class last semester. I didn't get very many questions because they had so many attempts. They just kind of always worked themselves to the right answer. If you have any questions, feel free to bring them to class. All right. All right, that being said, on to all the questions, we're going to kick off an integration review. So today I really want to go through what is essentially chapter 5 from the text, which is an introduction to integration. So coming into Calculus 2, you should have started integration. You should have defined the definite integral and gone through a lot of these steps, seen that it's area in the curve and all these kind of intro steps, and gotten about to the point where you really need to use integration a lot or use some complex stuff. That's really what Calculus 2 kind of kicks off. But what I find is that we've heard all this stuff, but we're not very strong with this stuff. We really want to be strong with the basics before we go on. So I'm going to go through 5 sections today. No problem, right? We'll just zip right through. But that's not usually very productive, right? Zipping through 5 sections doesn't really do any good. So the goal here is not to reteach all this stuff. This is stuff you should have heard before, but it's to point you out the areas you need to work on. So we're going to go through some stuff from each section, and you'll say, okay, 5.1 makes sense. Everything he said there, clear as a bell. 5.3, boy, he was talking, and I didn't know what language he was speaking. Right, that tells you to go back to 5.3 and review that stuff. Okay, and feel free to bring questions for tomorrow. But that's the idea here, is to go through everything kind of broadly so you can identify your weaknesses. Okay? So these are the sections: approximating area into the curve, and then the definite integral. This is basically what is integration. 5.3 is the fundamental theorem of calculus, which essentially is how we're going to do the computations. Working with integrals is the application section. It kind of tells us if we're going to do this stuff, what's the purpose, what can we actually use it for. And then lastly, substitution is the first real technique that we're going to have for doing integrals. So, 5.1. In 5.1, we introduce sigma notation. So hopefully you've seen a little bit of sigma notation. That's the sum notation, how to use it. So for instance, if I said the sum from I equals 2 to 5 of 2I, what does that equal to? Go ahead and take a second and write it down on paper. This is kind of the trend of class. I'll put up a problem, and I really want you to work through it, not just come home. And when I do this, this is not some sort of quiz. So if you're stuck, I don't want you to just sit there until we do it. I want you to look at your neighbor's paper or tap them and say, hey, how do we start this? Or raise your hand. Feel free to talk about the problems up here like this. So you get done, check to see you got it right with your neighbor and that kind of stuff. And please understand, too, that people are coming into this class with a broad variety of backgrounds. Calculus is taught a lot of different ways and a lot of different courses. So some people will have never seen sigma notation before, right? Right? And some people will have used this a million times. All right, so what we got here is, all we do is we write out this piece, this value, and we plug in I equals 2. And then we add it to that same thing when I equals 3, so on and so forth. So I would have 2 times 2, plus 2 times 3, plus 2 times 4, plus 2 times 5. All right, I just write this over and over again with sums in between, and I go from I equals 2, and I count up by 1s all the way to I equals 5. Here I would get 4 plus 6 plus 8 plus 10, which is 28. Something to note about me. I have a master's in applied mathematics. Sometimes I can't add. So please check my work up here. Right? Feel free to say, hey, I don't think that 4 plus 6 is 11 or something. So feel free to interrupt. All right, any questions about the first one? Have we seen the notation before? Any questions? Okay. Then the section introduces the idea of Riemann sums, specifically the left sum, the right sum, and the midpoint rule. And so these are different ways that we can approximate areas under curves. So a typical question might look like, approximate the area under this function, y equals x squared, from x equals 0 to x equals 2, using one of those techniques. So here we're going to say using the left-hand sum rule, and then I tell you how many intervals we want to use, and I'm going to say 4 intervals in this case. All right, so approximate the area under this curve using the left-hand sum rule and 4 intervals. Once again, the goal here is to show you all the key topics, see what you know coming in, right? If you look at that and say, left sum, what was that again? You definitely need to go to chapter 5 in a little more detailed review. Of course, the whole book. How do we do sums? Break up that interval into a couple pieces and find the area of rectangles underneath this thing. So you do stuff, see if you can draw that picture. Find the area of those rectangles. I encourage you also to write out your explanation with sentences, all that kind of stuff. So a bunch of boxes to approximate the area. Does this one work? Does that look good? That's a bunch of boxes to approximate the area. Does that work? This would be the right-hand sum. Right, the idea is I'm going to make a rectangle over each interval, but there's lots of ways I can approximate the height. For this interval, I could use this as the height, I could use this as the height, I could use this as the height, I could find an average of the two, I could do all kinds of things. The left-hand rule just says use the left side of each interval to be the height. And just add up all of those rectangles, the areas. So I can really say, what's the area of that first box? 0, right? A height of 0. Woohoo. And what's the area of the second box? Well, it's a rectangle. It's base times height. Now, the way I've divided up my interval from 0 to 2 into 4 equal intervals, I should know that distance. What is the distance of the base here? What is it? 0.5. And how did you get that? Absolutely. We take the total distance of the interval, or the distance from the left-hand side to the right-hand side, and divide by the number of intervals we want. All right, so in general, we're doing this thing. We're trying to find the heights. That's the function value at each of our little positions. All right, so if I said this is x sub 0, this is x sub 1, this is x sub 2, so on and so forth, I'm taking the height times the width of the base. All right, that delta x is a little change in the x value. It's the length of the base there. Now I just want to add those things up. That's what that kind of fancy formula looks like. And what is delta x? Well, we just heard that it's that interval length. It's the final point minus the initial point divided by the number of intervals. In this case, it's 2 minus 0 divided by 4, which gives us a value of 1/2. So now I want the area of the second box. I know the base is 1/2. Now I just got to figure out the height I'm using. Well, the height is just the distance to the curve at this point. Well, if I started at 0, and each of these intervals is a quarter, that's a quarter. What's the height at x equals 0.25? Well, it would be 0.25 squared. All right, so if this is, it's a quarter, oops, I'm sorry, that's a half, not 0.25, half, sorry about that. That's 1/2, that's 1, this is 3/2, and that's 2. Those are my positions here. Then this area would be the function evaluated at 1/2 times my base, which is 1/2, plus the area of the next box, this one, which would be the function evaluated at 1 times my base. And then the last one is the function evaluated at 3/2 times my base. My function is x squared, so this is just 1/4 times 1/2, plus 1 times 1/2, plus 9/4 times 1/2. So I got 1/8 plus 4/8 plus 9/8 is 14/8. Right. So what do I got? I got 1 3/4. Is that right? Confirm or deny? And when I say, does that look good, I'm really asking because it's very easy for me to make some little mistakes myself here. So hopefully we've had time to work on it, and some people have also gotten the same answer. Well, this is the left-hand sum approximation to the area of the curve. And does it make sense? Well, let's see. If I kind of drew a little square here, well, the height here would be 4. So the area of that big rectangle would be 8. I kind of drawn it pretty poorly here. I went up way too far here. Really, this is going to go shoot up. But it's definitely less than 8. It's bigger than 0. I could draw a diagonal. I could also say it's less than 4. So yeah, that's somewhere in the ballpark area. I didn't get like -3 or I didn't get 20. So that's good. That seems to make sense as an answer. The next question would be, is this over or under the real answer? Under, right? We can see that because of the boxes we've drawn. And in fact, if we use the left-hand sum and our function is increasing, that left-hand sum will always be an underestimate. If we use the right-hand sum, if instead I use these boxes, then I would have an overestimate. Right? If the function is decreasing, those would switch. And you can memorize all those little rules, or you can just look at that picture. Right? Teach yourself how to draw those pictures. Those are important pictures. Are any questions about the left-hand sum? Hopefully that's a quick refresher. Hopefully from there you can do the right-hand sum and do that midpoint rule as well. Now, let's see, what do we have here? We have integral of x squared. You guys have probably done some of these integrals before. So if I actually wanted to integrate x squared from 0 to 2, anybody know what that integral would be offhand? This one?
Would be 1/3 x cubed.
Yep, x cubed over 3, evaluate from 0 to 2. We'll talk more about this more. So 8/3, absolutely. So that's 2 1/3. I'm sorry, 2 2/3. Right? And we said it was 1 3/4. It's not very good, is it? How would I find a better approximation? What could I do to improve my approximation here?
Take both the right left-hand sides and then average them.
Absolutely, that would be better, right? It would still probably be a little farther a ways, but it would be better for sure, right? But what if I really wanted to get close?
You could minimize, or you could maximize how many different parts you put up.
Absolutely. I mean, I used 4 intervals. It'd be better if I used 20. It'd be really good if I used 300. Not going to do that by hand. It'd be very easy for me to program that in Mathematica and do that. And then I could use a very large number. And the bigger the number I use, the better my approximation should be to the real thing. All right, so if we used 1,000,000, we'd be pretty darn close. If we used 30 million, we'd be really, 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 really close, right? And so the idea as we transition to 5.2 here, the definite integral is here we're taking the limit as the number of those intervals goes to infinity. Or also kind of in the same light as that width of the interval goes down to 0. Right? Because the more intervals we use, the size of them is going to shrink here. So all we do is just grab what we did before. We said that's the height on one of the sides of my interval. That's the thickness. So that should be the area of one box. And all I did to approximate my integral was add them all up. And before we add them up from I equals 0 to I equals something. But in general, if I added them up until, like I use so many intervals, and I look at this as the limit as this thing went to 0, then this should give me an exact value. And that's really what we say. We say if that limit exists, then that is the area under the curve, right? We dub that the actual area. And we call this thing, give it a name, the definite integral. All right, so we're going to have a quiz tomorrow on integration review at the very beginning of class. So we're going to do kind of an integration review today. We're going to talk through all this stuff. There's a couple big things. You have to be able to write this out. This is the limit definition of the integral. All right, Calculus 2 is about a whole bunch of integrals. So you absolutely have to know the limit definition. So you should be able to write that out. Now it looks a little ugly. But remember, you should be able to draw the picture to get this thing. Right? Just draw a graph, draw a little function. Here's A, here's B. How do I approximate? I draw these little rectangles underneath it. What's that area? That's the function evaluated at some random spot times the thickness of the base. I add them all up, take a limit, and I'm home free. Okay? So that's how you want to be able to kind of generate this. Okay, so 5.2 talks about that definite integral definition, how it really is giving us the area under the curve. So they do some calculations here. They actually calculate the limit of some sums, which is challenging, which is not very fun. Right? But they do that in this section a little bit. And they talk about some of the properties. What are some of the properties? All right, here's a bunch of them. We're going to finish them. So take a second and see if you can finish the properties. Complete the property statements. And of course, I'm being a little sloppy here. No, your book is never sloppy. Your book, all the details right in there. I'm going to be a little sloppy. I'm not going to say, for some continuous function f on some real interval from a to b. I'm not going to say that every time. Those assumptions are going to be there. But I really want to talk about the core content and let the book really hammer out those details. Remember, it's not about memorizing these properties, it's about really trying to think through them. Finding the area under the curve.
What about the first one?
If I integrate from A to A, how much area do I get? Zero. Right? So if I integrate from A to A, this is automatically 0. If I'm adding up all the area from here to here, there's no area. So this is going to give us 0. All right, now this one's a little bit quirky maybe, right? We have to kind of understand how they want us to treat area here. So if I integrate from B to A, if I go like this instead of like this, well, really, you might think, well, the area doesn't change, but we're going to change the sign here. We're going to give that value for the definite integral a negative sign. Right? So if we integrate from right to left, it's the negative of the value of the integral from left to right. Okay? Now, does that mean the area is negative? You count it backwards? No, area is area. Area is always a positive value, right? But this definite integral will give us a negative value when we integrate in this direction. Okay? So there's two different questions I could ask. I could ask, what's the area under the curve from A to B? And you have to know that that's a positive value. Or I could say, what's the integral from B to A? And you could find this positive area, and the answer you would give me is the negative of that number. Okay? So. All right, the next one, the integral from A to B of the sum of two functions is what? Absolutely. I don't know what you guys did in school, but I used to have to chant this all the time. Like we were like monks at a seance. I don't know. It's like the integral of the sum is the sum of the integral, and we have to say it like 100 times. But it's good. It sticks in your brain that way. The integral of the sum of two functions is the sum of the integral. The integral of the sum is the sum of the integral. And the same thing for the derivative. The derivative of a sum is the sum of the derivatives. And so when you get used to saying it, you can really make sure that property sticks. The next one, the integral of a constant times a function is times the function. Yep. Constant times the integral of the function. That's a nice one. You probably use that one in an application a lot. You get to pull out constants. Right, the integral of 2 times something, that 2 can come right out front. Look at that property. And the last one kind of goes with the picture here. The integral from A to C, if I add up all the area from A to C, it's the same thing as the integral from A to B plus the integral from B to C. You can just stop anywhere in the middle. Stop and start doesn't change the value. Integrate from here to here, and then from here to here. Okay. Any questions about those properties? Let's use them. Here's a bunch of problems. Here's a bunch of problems that you might see in that section. Let's talk about the first one here. We're going to talk through some of these. Now the first one you might be able to do just because you've seen integration before. But at this point in the reading, they haven't done any actual integrals. They haven't used the fundamental theorem of calculus yet, like we just kind of cheated a little bit ago. So if I couldn't use the fundamental theorem of calculus, how would I calculate this thing? If I can't integrate negative x and integrate 2, how do I find this integral value? Any ideas? Set? Absolutely. I can look at this as a area underneath some function. What function am I talking about? This function. Y equals negative x plus 2. That's a line. It's a line that has a y-intercept of 2 and a slope of negative 1. And then the integral of that thing, the area underneath that curve, is just the area of this triangle. So what is that integral equal to? Well, it's equal to 1/2 the base times the height. And the base is 2, and the height happens to be 2. So whereas I can see a function, say find the area, and you might take the integral. When you see an integral, you should be able to visualize the area underneath some function, where that function is that integrand piece. Remember, this thing is called the integrand. It's the thing we're integrating. Same thing for this one. What's that function, though? Well, if we started with this thing, what's this look like? Looks like a circle. Circle of radius 2. If I solved that for y, I would subtract the x squared. I would take the square root, and I would get y equals plus or minus the square root of 4 minus x squared. Okay, that looks like what I got. So what that integrand is telling me is that we have the bottom half of a circle. I'm integrating that from 0 to 2. They must be talking about this thing. So I could say the area of the whole circle is pi r squared. I just want a quarter of the circle. Is my answer pi? Not pi. What is it? Negative pi. I can look at this visually and say, oh, it's this area is what we're talking about, but this is the area under the curve. And that's also, we consider that negative when we do the definite integral. Is the area negative? No, the area is some positive value. This area is pi. But if I integrate from here to here, if I integrate where I have my function below the axis, I get a negative value. Right? It kind of adds it up like negative area. Okay? So I know that definite integral has a value of negative pi. Okay. Now we have some other ones here. If the integral from 0 to pi is if the integral of sine of x from 0 to pi is 2, then what's this integral equal to? 4, right? I'm just saying it's a constant. I can just pull my constant out. And if this piece is 2, then I get 2 times 2. This is just using some of our properties. What about this one if we just look at it visually? There's a kind of sketch of sine. I integrate from negative pi to pi. 0, absolutely. I'll get 0 here. It's like I have the negative area and the positive area canceling each other out. I can really see that, but the next one I'm integrating from negative 1.2 to 1.2. What's that one going to be? Also 0. And so it doesn't really matter if I have this thing, but if I just go the same distance on either side, it will cancel each other out. Because this thing is, well, it looks like it has some sort of symmetry across that, right? In fact, this thing has symmetry about the origin, because this thing is an odd function. Right, so hopefully in Calculus 1 you talk about odd functions and even functions and define them. And we want to know the special properties of their integrals. Right, so if I integrate from negative a to a of an odd function, I get 0. If I have an even function, like cosine, it's just a symmetric about the y-axis, and I integrate from negative a to positive a, what's that property? What is it? 2 times the integral from 0 to a. All right, so I don't have to integrate from here to here. I can just double this value. Right? I can just take 2 times the integral from 0 over to that value. Okay? Once again, go back and review those properties for even and odd functions. All right, so we have those little tricks for calculating stuff, right? We can use some areas and we can use some properties of even and odd and use these properties. It doesn't really give us a whole lot of tools, though. I mean, if I want to integrate even something like we've been looking at, sine of x, but from a 0 to a 1.4, it's like, ugh, How am I going to do that thing? Well, I could do the definition. The limit of some sum is the sum, the limit as delta x goes to 0 of the sum. That's going to be hard because I'm actually have to find the limit of this sum, and that's a very theoretical process a lot of times. I have to show the limit exists and what the limit is converging to and all this other stuff. It's hard to do, so it's not what we do. Right? Instead, we have our big tool, the big hammer we use to actually do integration, and it's the fundamental theorem of calculus. This will also be on the quiz. The quiz will look like state the limit definition of an integral, a definite integral. We'll say, what is the fundamental theorem of calculus? This is also will be on here, big old star. So what is the fundamental theorem of calculus? The integral from a to b of f of x dx is equal to? Absolutely. Big F of b minus big F of a. But when we write that down, we have to include another piece. Right? We can't just kind of throw letters around. Right? So now we need to say where, what is this thing defined to be? The derivative of this piece is our function. Right, it's not the derivative of little because that would almost be too easy, right? If you just grab this thing and take the derivative and get to that out, it'd be really easy. We're trying to find the antiderivative, the function whose derivative gets us back to here. Okay? And then we'll just practice with our other notation for the derivative, right? Good old Leibniz notation. It says the derivative of capital F with respect to x. This is the fundamental theorem. Sort of the fundamental theorem. I mean, this is what we all think about when I say, what's the fundamental theorem? This is the piece that should jump into your brain. This is the thing we actually use to calculate definite integrals. But turns out this is actually the second part of the fundamental theorem. There's actually a first part as well. And the first part, which is kind of the annoying part, don't tell the other mathematicians I said that. Right? The integral from a to x of f of t dt is equal to capital F of x. It says this thing is always true. And this is kind of the underpinnings of the indefinite integral. In fact, another way we can write this would be that if we have that capital F piece and we take the derivative of that capital F piece, this is the derivative of the integral from a to x. So here's how we kind of defined it. Now we're taking the derivative of it. And you write this down and people get kind of annoyed. They say, really? Isn't that where you just wrote up here? Right? Where the derivative of the capital F is for this thing? But this is saying something kind of subtle in between. It's saying that we're trying to find this antiderivative piece here. And there actually always exists an antiderivative piece. The antiderivative is this thing. Because the derivative of this thing gets me to f of x. So there always exists an antiderivative. And you might have heard in some classes, well, this function doesn't have an antiderivative. Not actually true. There's always an antiderivative. There might not be an elementary antiderivative. The antiderivative might be obnoxious. The antiderivative really might be the integral of something that looks like this. Right? So it doesn't really help us at all. It doesn't really useful. But there always exists an antiderivative, and it's this piece. And it actually gives us two things. One, it says we can numerically approximate this area all the time. But it also kind of shows us something we like to see. And the first one, if I kind of rewrite this, like I know that the derivative of capital F prime is equal to this thing, I can almost rewrite this like this. And that's me plugging in that little f. And the result is f of b minus f of a. It's kind of like if I integrate a derivative, the derivative goes away. And this kind of looks like, well, if I take the derivative of an integral, I just get the function. It's almost like these things are inverses. They're not really inverses, because there's this weird constant thing that keeps floating around. But they kind of do that. They kind of act like that. They kind of undo each other. And these are the two theorems that really relate those two things. They relate the derivative to the integral. Okay, but of course we're mostly concerned with actually using this thing. So we should be able to do problems like this. So try these two. Now we're into 5.3, 5.4-ish. Once again, this should be a guide for your own review. Like I said, it's important to come to class because we'll be doing these problems all through class. It gives you a chance to ask questions. But also, this class is about an hour and a half. You might think you can watch an hour and a half long video. Trust me, it's tough. Grant might have been. I got my integrand 2x. I need to find my capital F of x. The thing whose derivative gets me that. What is my capital F thing? X squared. And we can check. It's the derivative of capital F. It's going to be 2x. So we got it. So then how do I apply my fundamental theorem? This is going to be f of 3 minus f of 1. So this is 3 squared minus 1 squared. And looks like I get 8. Now I need a function whose derivative is cosine. Derivative of what gets me to cosine? Sine. So this should be sine of pi over 2 minus sine of 0. Sine of pi over 2 is 1. Sine of 0 is 0. That's 1. And we should always be double and triple checking all our values. Check them with your calculator to make sure you're right. Check them graphically. This looks like this piece. Well, it looks like half of the arch, right? Half of the full arch, which we just said was 2, so I expect this to be 1. I'm pretty happy with those answers. Now, I realize I haven't paused for questions in a while, so any questions about this or anything we have covered so far? Yep.
I discovered late in the semester last night that I was getting marked down and I'm showing all my work.
Mm-hmm.
How close do you need to teach? Like, I probably would have shown half that and still didn't.
Yes, for these, I expect to see little to no work. Right? It depends on the problem. Right? If you can do it mentally, I think that's fine. But if it's pushing it, I might have you come in and show me that you can do certain things mentally, right? And I would encourage you not to do it. If there's obvious steps, you need to do the obvious steps. Don't write it down on a scratch paper and then translate the answer over, or just go through the logical steps on paper. Okay. Yeah, I mean, I would say like for this one, you don't necessarily need to show any steps. But at the same time, I would. Right? If I was doing this problem, I would just say, okay, well, I know that's going to be x squared. I know this is going to be 9 minus 1 is 8. Right? That might be all the work I show. And of course, I could probably do all that mentally from the beginning, but writing down the steps is just good to clear your mind so you don't make mistakes along the way. Okay? Good question. Other questions? You also are allowed to use calculators. So on the exam, if you use a calculator, that's fine. I'm going to have you annotate that and say, with my calculator. Then I just know. But you're welcome to do that too. So you can imagine I'm not going to have a whole lot of these on there, right? So I can't really tell whether you just did that mentally or did it with your calculator. So. Other questions? Any questions so far? Yep.
I have a guy in my computer on my phone.
Mhm.
Some instructors will be able to use it, some haven't.
No, I can't let you use that. It can't be internet accessible. That's my restriction. At the same time, I know that the math department probably has a couple extra calculators, so if you don't have something, you can always request to borrow that for the exam, but then of course you got to know how to use it. So if you have an emulator, you could use it and then just borrow one if you can find one. But,
You won't all over the library.
okay. Yep. No, because it'd be too hard for me to monitor whether you're on Wikipedia or accessing PDFs or something like that. I know a lot of stuff you can actually do on a T9 too, but other questions? Everybody uncomfortable? Okay. All right. 5.4 really gets into applications of the integral. What are we going to use some of this stuff to do? And one of the uses they stress is the average value of function. And so they have a little definition. The average value of the function is 1 over b minus a times the integral of the function from a to b. So once again, we can memorize that formula, but I really encourage us not to. Right? What is this thing telling me? It's telling me to take this piece, the area, and spread it out over the interval. Right? It's like you're smushing and flattening. Right? If I have x squared from 0 to 2, the average value is going to be taking all this area and spreading it out over that whole interval. Spreading it out so it's nice and flat over that interval. Probably won't look like that. It'll probably look more like maybe like this or something. I don't know. But that height I get to if I were to flatten all this area out, that height is the average value of the function. This is how we calculate it. Huh? So go ahead and find the average height of sine of x over the interval from 0 to pi. See if you find the average height of the curve, the average value of the function here.
By height, you mean the y value?
Yeah, so really it's kind of saying the same thing here. The average height of the function is the average value of the function, because it's the f value you're getting at this function. So by height, I mean distance from the x-axis up to the function value. So how do you find the height at x equal 2? You take the function of value in at x equal 2. Take sine of 2. Sorry. I'm just glad I wasn't the first one. Sometimes that's all I want to do. Very important that you guys turn your phones on vibrate. All right, so I'm just going to apply my definition here. I'm going to find all the area from 0 to pi. This is me finding all the area from 0 to pi. And I'm going to spread it out over my interval, 0 to pi. So I'm going to take 1 over pi minus 0. What's the length of pi? We've talked about that integral a couple times now. What is the value of that integral? Integral under one arch of those trig functions is 2. It's just one you see a lot. So, but you could actually, chug it out here, and you'd get a value of 2. So this turns out to be 2 over pi. If we think about what that is, well, it's 2 divided by 3.14. Anybody want to chug that into a calculator for me real quick? 0.64. And so if we think about what the sine looks like, look at that. This is 1. Turns out the average value is 0.6. So there's half right about here. This is the average value of that function. Of course, my drawing is kind of goofy there, I'm sure. But all right, any questions about that one? Okay. So the other thing related to that is the mean value theorem. This is an important theorem conceptually, right? If you want to, in statistics, this is very important. It's also very important to prove a lot of things. It's one of the core tools of an analysis course. And so that means it must be really difficult, right? But it's really not. It just says that this average value we just found, the actual function has to hit that value at some point. It actually has to take on that value. So there is some spot, some value in between our intervals. So before this was from 0 to pi. There's some value in between 0 to pi. Maybe it's 1 or 2 or 3 or 2.8. Somewhere in between 0 and 3.14, blah, 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 blah. There's some spot inside where the function actually becomes that height of 0.64 or whatever it was. And that's all the mean value theorem says. You know, they write it in fancy math talk, but all it's really saying is, zip this up a little more, it says if this is the average height right here, the function actually hits that height. In fact, in this case, it hits the height twice. Okay? That's all it's saying there. That's just a key theorem to have in the back of our minds. And the last section covers substitution. So substitution is the first real technique that we should have seen and need to work with. So this is one that we're going to practice a little bit tomorrow as well before we launch into chapter 6. But we'll kind of go through it real quick. They have a big fancy definition for it. And this is kind of the equation that generates it. But we don't really use this equation to do substitution. But it's there. It kind of guides us. Says these two things are there. And it's actually not too hard to prove. All you do is you take the composition of two functions. You take the derivative of it. If you take the derivative of a composition, what's the derivative rule you have to use? Chain rule. So if you use chain rule, you do a little bit of algebra, you integrate, boom, there you got this thing. And while we use this thing, we say, okay, I'm going to run into integrals that look ugly like this. And I know they're equal to something simple like this. And so all we have to do is get the notation, right, to go from here to here. Because I have functions where I have some inside function whose derivative is also a factor. And when I can see that, I have a function inside as a composition and the derivative is a factor, then I can replace this function with u. And it simplifies very nicely to this. So I'm looking for a function whose derivative is a factor, and the process says let that thing be u, and we'll be able to write a nice simplified form. So here's my steps. These are also in the book, and we'll go through kind of a quick example of this. So I'm running very short on time here. So just a quick example, and then you can refresh yourself with some practice problems. What I always tell all my students when I finish Calc 2 is that at the end of a lot of these chapters in the book, there is the review page, right, for integration techniques, and they have a billion integration techniques. We're going to cover that in chapter 8, I believe. When you end this class, you should photocopy that page and the key to that page. And every other semester from here on out, so the day before the semester starts, just take out that sheet and just go through a bunch of integrals. It will pay a lot of dividends later. All right, so how do we do this thing? I need to see if substitution will even work. I need to see, do I have a function inside whose derivative is a factor? I do. I have x squared, which is inside some other function. It's the composition cosine of g of x in here. And the derivative of this is 2x. That looks something like this. I don't care that there are multiple different. That's okay. The idea is I have a derivative of something like x. And here I have something that looks like x. I have an inside function whose derivative is a factor. That tells me to let u equal that inside function. And then I know I can write a simplified version. To get to that simplified version, all I do is take the derivative of u, and then I solve it for dx. So I take the derivative of u with respect to x. What is this derivative here? (2x), thank you. I'm going to solve that thing for dx. I'm going to multiply both sides by dx. I'm going to divide both sides by 2x. I'll get this thing. And I'm just going to chug everything into my integral. integral of x times the cosine of, well, I'll get rid of the x squared. I'll get rid of the dx. And look at that, those x's cancel out. That's great. So I don't know how to do an integral that has x's and u's in it. So I need all that stuff to cancel out. I'm just left with the integral, looks like this. This is a much easier integral to do, and that's the whole point of substitution. Take an ugly integral, turn it into a nice integral. Now I can use my property. You don't have to show this work in general. I'm just going to do it here. Pull out that 1/2. Now I know that the integral of cosine of u is sine of u. And of course we have our little plus constant that we're not going to forget later on. So that's one quick application of substitution. Unfortunately, we went through that pretty quick. So tomorrow's class, we're going to start off with that preparation quiz. We'll talk a little bit more about substitution, do a little more practice problems. The big idea for tomorrow is to get your My Math Lab account all set up. I'm going to go and make sure that code is working in the next 20 minutes. I will get that taken care of. After that, you can log on to My Math Lab, look through the modified review. I'm going to tweet that as well. Go ahead and read section 6.1 and 6.2. We're going to finish substitution, take our quiz, and then go through 6.1 and 6.2 tomorrow. And I have office hours right now if you have any questions.
Questions.
Yep.
First off, so all the homework is posted on the what's it called, Canvas account, and that's the only source of homework.
The only homework is going to be on the Pearson page, the My Math Lab.
Okay. How does labs in past classes? They kind of the lab day for calc I took was just it was another class day. It was another lecture, and we'd occasionally have a lab sheet. We'd have to do.
Yeah. So here the lab is totally online.
Okay.
You should have received an email.
I have.
Okay, great.
Yeah.
So you just follow that email. It'll bring you to a new Canvas page.
Okay.
Stop.